8.7, pH and pKa. So the outcome is I can explain the relationship between the predominant form of a weak acid or base in a solution at a given pH and pKa of the conjugate acid or pKb of the conjugate base. So we're going to be looking at the relationship between pH and pKa, and based on how those numbers compare, we can predict whether we have a weak acid or a weak base in solution, which form would be predominant. So the protonation state of an acid or base can be predicted by comparing the pH of a solution to the pKa of the acid in the solution. We can make a likewise comparison with bases using pKb. So when the pH of the solution is less than the pKa, that means that the acid form is going to be the predominant form of that compound. So it will have a higher concentration than the base form. When the pH is greater than the pKa, the base form is going to be in higher concentration in the acid solution. So we have a buffer solution that is created using the weak acid HF, which has a Ka of 6.30 times 10 to the minus 2. And it also contains the salt NaF. So my buffer system here consists of HF, and the conjugate base to that is F minus. So these two things together are going to make up my buffer system here. So we want to predict at different pH values whether the predominant form of this is going to be HF, the acid form, or if it's going to be F minus, which is the base form. So first things first, we should take the negative log of the Ka, so we get our pKa, and that gives me a pKa of 3.2. So if the pH is less than 3.2, then that means that we're going to have mostly the acid form, and if the pH is greater than 3.2, it's going to be in the base form. So for our first one, at a pH of 1.5, HF is going to be the predominant form. At 3.2, notice that's the same as the pKa. Then the HF and F minus concentrations are going to be the same. This is just an equimolar buffer solution, and when we have a buffer solution that is equimolar of the acid and base component, the pH is just the pKa. At 4.6 and 7.2, the predominant form is going to be F minus because our pH exceeds our pKa. Now, this is useful information for selecting an indicator whenever you do an acid-base titration or just any reaction where you need to use an indicator to track pH. So there are two common methods for determining the equivalence point of a titration. We can monitor the pH using a pH probe, and so we get, our curve that looks like this, our angry snake curve, and right in the middle of that vertical component is my equivalence point. Or we can just use an acid-base indicator that will change color at the pH of the equivalence point. So that means you have to know what you're reacting and what the pH is going to be at the equivalence point. So acid-base indicators are weak acids themselves, and they're generally represented by HIN for indicator, meaning that the concentration of the indicator components are defined by an equilibrium. The color of the indicator is different in its protonated versus deprotonated forms. So for a typical acid-base indicator with a dissociation constant Ka, the color transition occurs within plus or minus 1 unit of the pKa. So here we have an indicator that has a Ka of 1 times 10 to the minus 4. So which of the following are going to be correct? So here we see that we have the indicator, which is written as a weak acid. And this is just present in water. So that's the strongest base that I have to receive an H plus from the acid, leaving behind IN minus. So we know that when the predominant form is HIN, in its acidified form, it will be yellow, and in its basic form, it will be red. So the predominant color in its acid range is yellow. So that makes sense because HIN is going to be yellow. Ion minus is the dominant form, so A works for us. In the middle of the pH range, its color change for a solution containing the indicator will probably be orange. So when you're in the middle of its pH range, remember that's plus or minus 1 unit of the pKa. When you're at the pKa, the acid and base form exist in equal quantities. So this would probably look like it was orange. So we agree with statement B. At pH 7, a solution containing this indicator will be red. So in its dominant form, ion minus is going to be red. So if we write our Ka here and we find our pKa, the pKa is 4. So our pH is greater than our pKa, which means that the indicator is going to be predominantly in its basic form. So it's going to be red. So we agree with point C as well. At pH equals 7, most of the indicator is in its unionized form. We disagree with that for reasons we've just explained in C. So because our pKa is 4 and we are at pH 7 and it's greater than our pKa, the predominant form is going to be the base form. So we disagree with point D. And the pH at which the indicator changes its color is going to be pH 4. So that makes sense for us. The pKa plus or minus 1 would be somewhere between 3 and 5. So we would see within that range, pH 4, we would see the color change occurring. So for each acid-base pair, we're going to predict if the pH at the equivalence point is less than 7, equal to 7, or greater than 7. And then we're going to suggest one of these indicators. So we have indicator A, B, C, D. We have their color change, pH range, and their acidic and basic range color. So starting off with HCl and NH3. So HCl is a strong acid and NH3 is a weak base. So what this means is that this HCl is going to donate an H+, and we're going to form ammonium, NH4+. So my pH is going to be greater than 7 because I'm forming the base NH4+ at the equivalence point. So I'm probably going to want to use indicator B here because it will be yellow around that pH. So we'll see that color change there. Next up, I have HNO3, which is a strong acid, and I have calcium hydroxide, which is a strong base. So my pH is going to be 7. So I'm going to want to choose an indicator that is going to change color in that range. My next option, I have another strong acid. I have perchloric acid and sodium hydroxide. So once again, my pH is 7, and the best indicator is going to be choice C. Next up, I have a weak acid, and I have a strong base. So this weak acid is going to donate its H+ to form water, and I'm going to be left with ClO-. ClO- can accept an H+. So my pH here is going to be greater than 7, and ClO- is going to be formed here at the equivalence point. So I want to choose probably D, something that changes color during that range. And then my last one, I have acetic acid, which is a weak acid, and KOH, which is a strong base. So I'm going to form acetate at the equivalence point, which is a weak base. So my pH is going to be something greater than 7. So that means that we're going to want to choose an indicator that will change color greater than 7. So that's probably going to be choice D. Here are some reflection questions for you to think on. Explain how to select an indicator for a titration. And if the pH of a buffer is equal to the pKa of the acid used to make the buffer, how do the relative concentrations of weak acid and conjugate base compare?